Alright, welcome back guys. We're going to finish up 8A here. So we were talking about linear versus exponential, either growth or decay. And we had just finished this example in which we have this piece of equipment that's depreciating by $200 per year. So its value is decreasing by a fixed amount, and so that was an example of linear decay. Okay? And I showed you step by step how you could find it using the table, and then we also looked at finding it using that formula that I gave you above in the notes here. Okay. Alright, so let's continue. Let's go to part D here. So it says the memory capacity of state-of-the-art computer storage devices is doubling approximately every 2 years. So this is an example in which the time period or the time interval is not 1 year. Okay, it's actually every 2 years we see this doubling. So if a company's top-of-the-line drive holds 16 terabytes today, what is it going to hold in 6 years? Okay. First of all, let me say that 6 years would be 3 2-year periods. Okay. And then secondly, guys, what does it mean for something to double? If something is doubling, it's not increasing by a fixed amount every year. It's actually increasing by 100% of the current amount. For example, if you get a 100% raise, let's say you make $20 an hour, and you get a 100% raise, then your hourly rate is going to double. You're going to get another 20. Making you have a total of $40 per hour. Okay, so whenever you see this doubling, that means it's exponential growth. Okay, and the rate of growth is actually 100%. So let me put this in the notes here. Okay, so we're going to go with exponential. All right, and we'll work this out the same way. So we'll do time here. This will be for our calculations. And then over here, this will be the storage capacity at the end of each of these 2-year periods. Okay. So we'll start at time 0. So the storage capacity is just going to be 16 terabytes. I think it's abbreviated like that. And after that next 2-year period, and you could skip one of these if you want, but over that first 2-year period, then the storage capacity is going to double. So, in other words, you would say, okay, well, what's 100% of 16? Well, that's 16. Okay. And so if the initial is 16 and it increases by 100%, that's another 16. And that gives you a total of 32 terabytes. Okay. The nice thing about doubling, guys, is that you don't have to multiply by a decimal. Okay. Because we can double things in our heads easily. And then over that next 2-year period, it's 100% of now 32 terabytes, which would be 32 plus the original 32, okay, is going to be 64. So we're just doubling again, okay. And then finally down here at year 6, it'd be 100% of 64, okay, which is 64, and then 64 plus the other 64 is going to give us a total of 128 terabytes after 6 years, or in other words, 3 of these 2-year periods. Okay. Now, if you're using the formula from above, let's see if we can find it here. Here it is. See, it's the initial times in parentheses. Remember, this is similar to the formulas we used for compound interest. 1 plus the growth rate Well, if the growth rate is 100%, when you convert 100% into a decimal, it's 1, okay? And then we raise it to the power of time, okay? But in this case, it's not a number of years, it's a number of 2-year intervals. So we'd be raising it to the 3rd power, because 6 years is 3 2-year intervals, okay? So if I use that formula down here, which I am going to, the final storage capacity will be equal to the initial, which is 16 terabytes, times, in parentheses, 1 plus 100% as a decimal is 1. Okay? And then we would raise this to the 3rd power, because there's 3 of these 2-year intervals. Okay? So then this would become 16 times 1 plus 1 is 2 to the 3rd power. And if you remember your order of operations, you've got to do your exponent first. 2 to the 3rd power is the same as 2 times 2 times 2, which is 8. So this becomes 16 times 8, which is 128 terabytes. Okay. All right. So I know this one is maybe a little tricky because you've got to realize that when you double something, you're increasing it by 100%. If you increase something by half, you're increasing it by 50%. Okay. But anyway, all right, let's look at one more, and then we're going to move on to a critical thinking question. All right, let's look at E here. It says the price of high-definition TV sets has been falling by about 25% each year. Okay, so since falling means that we're talking about a process of decay. But the price of these TV sets is not falling by a fixed amount, it's falling by a percentage, okay, or a relative amount. And so this is going to be exponential decay. And it says if the price is $1,000 today, what can you expect it to be in 2 years? So I'm going to put over here exponential decay. Okay. So we're going to do this the same way, guys. Just label these, and you know, if you want, I would suggest or urge you to use the 2 formulas to calculate these. But if you want to use make yourself a table, that's perfectly fine. The final price of each of these years. Okay, so at time 0, the TV set is $1,000. Okay, but after that first 1-year period, then it's going to decrease by 25%. So we need to figure out what is 25% of $1,000. Okay, so again, you know, you convert 25% to a decimal, you multiply by 1,000, and you're going to get 250. Well, it's going to decrease by 250. So 1,000 minus 250 will bring the price down to 750. Okay. So over that first year, the price of these TV sets is going to fall down to 750. That's why, you know, when a new technology comes out, maybe it's not unless you're rich, of course, you know, maybe wait just a little bit for the price to come down. All right, and then from the end of the first year to the end of the second year, the price is going to fall 25% again, but it's going to be 25%. Well, I think my computer froze again. Hold on just a second. so hopefully the video continued recording. When I got kicked off, or my computer froze, guys, I actually had to change the password for my access to the PTC network. So anyway, that's why it took so long. Anyway, as I was saying here, over the second year, we need to figure out what 25% of the new price is, which is $750. So of course we're going to do this the same way. Convert 25% to decimal, multiply by 750, and I'm going to use the calculator for this. In other words, that's a quarter of $750. It is $187.50. Okay, so that's how much the price is going to fall over this second year. So the old price, which is $750, minus the amount by which it will fall, will give us, I don't know if I want to try to out at my head right now. We'll be left with $562.50. Okay. So that's what the price will be after 2 years for these television sets. Okay. Yeah, let's do this using the formula as well. So using the exponential formula, the final is equal to the initial amount, which is $1,000, times in parentheses 1 minus, this time though, because we're talking about process of decay. The rate of decay, which is 25%, is a decimal, and this is over a 2-year period, so our exponent will be 2. Okay. So for this, guys, just plug it all in the calculator exactly the way it's written. 1,000 times, in parentheses, 1 minus 0.25, close those parentheses, and then you can raise this to the second power. Hit enter, and we get the same thing, don't we? $562.50. Alright. Well, hopefully, guys, those are an ample supply of examples such that you'll be able to get your homework done. Next thing we're going to move on, these are just the solutions, by the way. Okay, but we already worked through all of this. I'm just going to skip this. Now let's come down here. The last part of this is going to involve some critical thinking. I'm talking about bacteria in a bottle. Okay, so there's lots of processes, guys, in the natural world that can be modeled using this idea of exponential growth or exponential decay. And the proliferation of bacteria is one of them. Okay. So let's read this very carefully. So suppose you place a single bacterium in a bottle at 11 a.m. and it grows, and at 11:01 it divides into 2 bacteria. These 2 bacteria each grow, and then at 11:02 they divide into 4 bacteria. So what do we have going on here? We basically have a doubling process. So this is an exponential growth process, okay, in which the rate of growth is 100% because each bacterium is doubling. And these 4 bacteria, they grow, and over the next minute, they divide into 8. So we just keep doubling, okay, and so on. Okay, so over the next minute, or the 4th minute, the 8 would double into 16, and then over the 5th minute, the 16 would double into 32. So it says now, suppose the bacteria continue to double every minute, and the bottle is full at exactly 12 o'clock. Okay? So the number of bacteria at this point must be 2 to the 60th power. Why is this? Well, because for one thing, there's 60 minutes, and this expression 2 to some power, when you have a process that's doubling, so after that first after that first minute, well, it's really, okay, so from 1101 to 1102, the bacteria, you're talking about the second minute here, okay? Wait a minute. So after the first minute, okay, the exponent that you're going to use represents the number of minutes. Okay, so after the, and we're using a 2 down here because we're talking about a process that's doubling. Now, if this process wasn't doubling, we would be using a different number. But anyway, so after 1 minute, 2 to the first power is 2. After 2 minutes, 2 to the second power is 4. Okay, and then after 3 minutes, 2 to the third power is 8. And these are the same numbers that we got, right? So if you continue to double the number of bacteria that are in the bottle each minute for a total of 60 minutes, then you can say that the number of bacteria in there at the end would be 2 to the 60th power, which is a huge number, guys. Okay, we may look at it here in a minute. Now let's continue, okay? So the bottle is completely full at 12 o'clock, so after 60 minutes, or after that hour, because they doubled every minute for 60 minutes, okay? And then this information here is not really important. It says, but the important fact is that we have a bacterial disaster on our hands. Because the bacteria have filled the bottle, the entire bacterial colony is doomed. Okay? Well, let's look at this question. The disaster occurred because the bottle was completely full at 12 o'clock. Okay? So the question then is, what was the time at which the bottle was half full? Okay? And so typically when I ask students this question, I'll give you a second to think about it. Okay, so we're starting at 11 a.m. with 1 bacterium. And then at 11:01, we end up with 2 to the first, or 2 bacteria. And then at 11:02, we have 2 to the second number of bacteria, which is 4. And the process just keeps going. So 4, 8, 16, 32, 64, 128, etc. Okay? These numbers start to get big real fast as the minutes pass. Okay? So after 60 minutes, or at 12 o'clock, well, let's see actually how many bacteria we would have. 2 to the 60th power. Oh, look, this gives us the answer in scientific notation. Do you guys recall that? Really large numbers have to be expressed, or more conveniently expressed, in scientific notation. I'm going to write this down. 1.153 times 10 to the 18th power, okay? Because of this E18. So what exactly is this number? And then we'll get back to this question. Well, remember your powers of 10. 10 to the third is 1,000. They go in threes. 10 to the sixth is 1,000,000. 10 to the ninth is 1,000,000,000. Okay, just keeps going on. Thousands. Okay. 10 to the 12th is 1,000,000,000,000. 10 to the 15th would be 1,000,000,000,000. 10 to the 18th would be 1,000,000,000,000. that prefix quin, if you've ever heard the term quintet, that's a musical group of 5 instruments. Okay, so you've got to go by these prefixes. Bi means 2, tri means 3, quad means 4, quint means 5. So this is over 1 quintillion. Or in other words, guys, if we were to write this in standard notation, since this exponent is 18, we would move this decimal to the right 18 places. So if we do that, what would we get? We would have the 153, that would move it 3 places, and then we need to move it 15 more, so we need 15 more zeros. There we go. So this is your number. You can put commas in here too if you want. So this is 1 quintillion, 153 quadrillions, how you would say it. That's a lot of bacteria, okay? Now, back to this question. When was the bottle half full? Well, what students typically tell me, they say it was half full at 11:30. Okay? And that's wrong. And the reason it's wrong is because the bacterial colony is not growing linearly. It's growing exponentially. And we as humans have a tendency to think about things, to frame things using linearity. Okay? We could see how many bacteria there were at 11:30. That would be the same as 2 to the 30th power. There's only that many. Okay, and this would be, let's see, this would be a billion. Okay, over a billion. That is not half. Okay, half of a quintillion would be basically 500 quadrillion. Okay, so the answer is the bottle is half full at 11:59. Okay. Now, why is this the answer? Well, because the number of bacteria in the bottle is doubling. Okay, so from 11:59 to 12 o'clock, the bacteria doubled. So for it to have doubled and completely filled the bottle at 12, it had to have been half full at 11:59. Okay, because if the bottle's half full at 11:59 and you double it, then it's going to be full at 12 o'clock. Okay, so this is an example of how our tendency to think in linear terms can really cause us to make erroneous assumptions. Okay. So anyway, this is a good critical thinking question. Now let's continue this. This is just the answer. Okay. Let's look at another question here, an extension. This will be the last one that we do, I think. So it says, how many bottles would the bacteria fill at the end of the second hour? Okay. So at the end of the first hour, the bacteria have occupied exactly 1 bottle. Okay. So if the bacteria is doubling and we have a bottle's worth of bacteria at the end of 1 hour, then that next minute the bacteria is going to double again and it's going to end up filling the second bottle. So we would have 2 bottles. Okay? And this would be the same as 2 to the first. Okay? So the process just repeats, except in this case it's more like we're counting bottles. The bottles are doubling. Okay? At the end of the second minute, we would have 4 bottles. Or in other words, 2 to the second power is 4. Okay? At the end of the third minute, we would have 8 bottles. I need to pluralize these, by the way. And that's the same as 2 to the third, which is 8. Okay. So if the process continues, guys, you'll end up with 2 to the 60th bottles. And we actually already saw what that number was. Okay. It was 1.159 1.159 quintillion. Okay, or in other words, it's basically 1 and move that decimal place to the right 18 places, so you'll end up with 15 zeros. Okay, so we saw it up here, so I'm not going to rewrite it. Okay, so anyway, that's how many bottles you would have after the second hour. Yeah, so it says at the end of the second hour, the bacteria would have filled approximately 10 to the 18 bottles. Okay. Now, if you're thinking about powers of 10, you can say, okay, well, we know 10 to the 6th is a million. 10 to the 12th is a trillion. So 10 to the 18th would be like a million trillion. Okay, that's another way that you could represent that number. A million trillion is the same as a quintillion. But anyway, all right. Last thing I will just mention here, that exponential growth leads to repeated doublings. And then with each doubling, the amount of increase is approximately equal to the sum of all preceding doublings. Exponential growth cannot continue indefinitely. After only a relatively small number of doublings, exponentially growing quantities reach impossible proportions. Okay, so that's the thing with bacteria, or you could even model like populations of rabbits in the woods. Their populations growing exponentially, and those models work for relatively small numbers, but you get to the point because they grow so fast that it becomes unsustainable. Okay. If you're modeling like a population of animals in a forest, they would grow. The population would grow so rapidly that it can't continue that same rate of growth, and the reason is because of food. They would run out of food. Okay, the forest or whatever would not be able to sustain them. Now, if you're talking about, and so there's a check there, okay, that's why the world isn't filled with rabbits, because they run out of food sources. Food becomes scarce, and that's what actually ends up limiting their population. But if you had some virgin woods that didn't have any rabbits in them, and you introduced a pair, then initially they would start to grow at an exponential rate, but then that would start to slow down as their food sources began to decrease. Oh yeah. Yeah, and the same goes in a petri dish. So if you have a colony of bacteria in a petri dish, initially the colony will grow at an exponential rate. But it'll start to run out of food, and you actually have another factor that comes into play. The waste products of those bacteria, those start to hamper the growth, or the rate of growth. It creates a very adverse atmosphere or environment for which the bacteria to grow in, so they don't actually continue to keep spreading at an exponential rate. So anyway, just a little bit extra on exponentiality or exponential growth. All right, guys, so that's the end of A-Day. So hopefully now you understand the difference between what it means to grow exponentially versus what it means to grow linearly. Okay. All right, and so I'll see you in 9A.